Welcome to my presentation on programming the Rubik's Cube solving algorithm and efficiency analysis of that algorithm. First and foremost, I want to say thank you for coming here today. I really appreciate it. This project has been a long journey, so let's begin. There's two basic questions I want to cover today. I want to try to answer. The first one is, what is the basic strategy behind implementing a Rubik's Cube solver program? Well, as you'll find out, it's a step-by-step process. It usually starts with creating a simple model and then progressing into writing the solving algorithm, and then maybe progressing a little further into adding modifications to your program and analyzing the efficiency of your algorithm. And then that brings me to my next question. How efficient is the solving algorithm that I wrote? When I talk about efficiency here, I'll be talking about the number of moves it takes for my program to solve a cube. I did an experimental test on the program I wrote, and I will share my results with you guys today. To give you guys a brief outline of the presentation today, first I'm going to cover designing the cube, a three-dimensional cube that the user can interact with and manipulate. Then I'm going to talk about the beginner's algorithm, which is a more simplified algorithm that does one thing at a time, one step at a time approach, but uses recursion and a case-by-case logic to solve the cube. I'll give you a little example of the a visual presentation of that later on. Then I'll talk about the implementation of the CFOP system, which was documented by Jessica Friedrich. Basically, the CFOP system, if you break it down, it's a way of solving the cube. A lot of the world record holders and really fast people use this system. It's trying to get the cross. Pretend this is you're trying to get a cross first, followed by putting in the first two layers. These two things I'm spinning, or this first two layers, trying to put them in at the same time, simultaneously, followed by Orion's last layer, which means getting all the top layer green, followed by permute last layer, which is fixing that layer, so it's finally solved. Then I will talk about the efficiency of each algorithm, again, talking about the number of moves it takes, and finally give you guys a little quick demonstration of my product that I made. So, in the very beginning, you have to make a cube that's functional, that can be used by the user. And so, I decided to create a simple two-dimensional model, as you see here. The first thing I did was design a class called Square that had data members such as position and color. And the idea was to manipulate this model and then reflect those changes in the three-dimensional model. It will become more clear in this next slide. For example, if I wanted to perform the move U, which means turn the up face clockwise, then this is what would happen. As you can see, the green cubes have moved, have shifted. The idea is to move the pieces, the squares, their locations, and then have a function or method that is continuously called throughout program execution that copies the colors of this current model and pastes them onto the three-dimensional model. So that's what I end up doing. And this is what the three-dimensional model looks like. Now there's a lot of numbers on here, and I'll briefly explain what they are. These numbers that are inside the squares are the index values of the two-dimensional array of squares. They're like ID numbers for each square. Then the numbers in yellow are the y-axis. If you were to paste the y-axis onto this model, that's what those values would be. And then the gray numbers are the x-axis numbers. Now, before I progress further, we'll explain that this face right here is the down face, and then this face right here is the left face, front face, right face, up face, and then back face. And before I progress further, also note that this position right here, 440, 170, is the 14, 2? That's that square right there in the up face in the lower right corner. Just that location. Don't worry about the 14.2, the gray square, but I'm going to just remember that location right there. I'm going to use that location later on in the presentation. But just know it's in the up face in the bottom right corner. So let's talk briefly about the beginner's algorithm. the beginner's algorithm uses two types of problem-solving strategies. Number one, recursion, and number two, case-by-case logic. For those of you who are unfamiliar with recursion, it's like going into a dictionary and looking up a word and then seeing that, well, the definition's not there. In fact, it says, see this word, like see word X, and you go to the word X, and then it says, see word Y, and you just keep going and going and going, trying to find the definition. That's the idea, but eventually you find the definition, and you're happy. That's the idea of recursion here, for those of you who are unfamiliar with computer science. But basically, the computer looks at the situation, and they perform an algorithm, which is it's kind of like a recipe. If you're trying to make a cake, you got to do this, this, and this, put it in the oven. It's just a sequence of steps, sequence of turns. And you might have to do that repeatedly, that process repeatedly, that algorithm repeatedly, in order to get the desired cube square where it needs to be. And then case by case, it's pretty simple to understand. The computer looks at the situation at hand and then performs the necessary algorithm based on the situation. Now I'm going to show you a little bit this recursive method here. It returns nothing. The whole goal of this method is just to solve the cube. But it accepts two integer parameters. These are the index values to the two-dimensional array. They just are ID numbers, essentially, for a specific square. Then followed is a one-dimensional array called position. It has two elements. The first element is the x-coordinate of the square, and the second element is the y-coordinate of the square. This function, get x and y locations, just fill the square given indexes, just fills that position array. Then we have a base case, which is usually involved when you have safe recursion. That tests to see if the cube square is in the right spot. If it's not, then we have the recursive case, and we do r prime, d prime, r, d, which is the needed algorithm. And then we make our recursive call because it's not satisfied yet that it's in the base case condition. Okay. So in the very beginning, you have this quick demonstration of this. This algorithm is going to do three function calls. So you see that star right there? That's the piece that we are trying to solve. First, it starts at 0, 11. That's the ID number of the two-dimensional array for that square. And then we have the return address, which is when the function is first called, it's called in a method called solve. So that return address is the line of code right after that where it's first called. And then we put onto the stack, the runtime stack, the value of the current position of that square with the star, 470, 200. Notice that it's not satisfying the base case, so you do the algorithm. I actually have it set up here. Do the algorithm, r prime, d prime, r, d. And as you'll notice, it's still not satisfied. It's in the lower right corner. So then we do it again. Same idea, push those values onto the stack, and then do the algorithm, r prime, d prime, r, d. But remember the recursive call, even though it's solved, it still calls the function one more time. And on the final call, the base case is satisfied because it's in that location I pointed out earlier, the 440, 170. And you were satisfied, and you move on to the next algorithm. So, we're going to talk a little bit about the CFOP system really quickly. It's not less interesting. It's more like case-by-case situational algorithm. So it involves a lot of programming for different situations, different cases that will arise. And one modification that I made was I made the cross on the bottom face, which made it quicker when doing the first two layers. And then multitasking, which is trying to put the first two layers in at the same time, followed by to-look OLL, means two algorithms were needed to orient the last layer, get all the last layer yellow, or whatever color was on the top. And then finally, to-look PLL, two algorithms required to permute the last layer and fix it. Okay, so I'll give you some quick results here. This is the really bad beginner's algorithm. It was very bad. 25 trials, and I didn't want to spend all day because I knew it was going to be, look at that y-intercept there. It's up there, and this table will show you, I mean, this is number of moves per trial number, and this table will make it more clear. The worst case for the beginner's algorithm, 312 moves. This is the experiment, so I don't know that this is the actual worst case, but it's what I got. And then average case, 252, 0.8, and best case 174. So it wasn't really good. So I decided to write another algorithm, and this is my better algorithm. I did 200 trials on this. It is a lot better. 164 moves for the worst case, 128 moves for the average case, 74 moves for the best case, and it was, as you can see, it's a lot better. It cut this by over 100 moves. So now I'm going to quickly do the demonstration on my product. I'm going to take this cube, and I need somebody to give me a string of moves. So, like for example, R, D, U. Is anybody familiar with the Rubik's Cube here? You know what I'm talking about, moves? Can you give me 10 moves? 10 random moves?
R, D prime.
R, D prime.
U.
U.
L.
L.
R prime.
R prime.
D. B.
B.
R. L.
Alright. One more?
D prime.
D prime. Okay. Alright, so I'm going to set this up and test out my program. So this is a quick demonstration of what my program actually looks like. This is the start screen. It just basically does that pattern shown by the 5x5 Rubik's Cube right there. If you had, I would do this, actually set it up like this, but that takes a long time, so I'm going to do a quicker thing. I'm actually going to just insert these moves into the program, and then I'm going to do it on this, and then I'm going to show you that it actually works. So, first thing is we do an R, followed by a D prime, followed by U, and then an L, and then an R prime, D, B, R, L, and then finally D prime. Alright, so I'm going to set that up right here. R, D prime, U, L, R prime, D, B. Okay, so I pretty much have the same cube right here. Red's in the center, blue's on top, yellow on the right. This time, orange is the cyan. It's a little different color scheme, but it's generally the same idea. Bunch of gray over here, so it looks correct. So let's try this out here. Do the quick solution, and probably speed it up. Okay, so how do you know that's real? Well, how do you know I just didn't change the colors of the squares? So bear with me as I go through this, okay? All right. E, F prime, R, D prime, F, D, U prime, B, B, L prime, B prime, U prime, B, L, L, U prime, L, U prime, L prime, U, D prime, E prime, L prime, U prime, U prime, L, U prime, L prime, U, L, U, back prime, U, back, U prime, D, E, R prime, U, U, R, U prime, R prime, U, R, E prime, D, D, U, R, U prime, R prime, U, U prime, E, D, R prime, U prime, R, E prime. Up halfway there. E prime, D, D, U, U prime, R, U, R prime, U, U, R, U prime, R prime, U prime, F, U, R, U prime, R prime, F prime, L prime, M prime, U prime, L prime, U, R, U prime, L, U, R prime. It's pretty small.
Yeah.
M, almost L. Pick a back case. E prime, D, D, U, R, U prime, R prime, U, R, B prime, R prime, U prime, R, U, L, M, U, R prime, F, R, M prime, L prime, U prime, U, R, M prime, L prime, R, R, D, D, R, U, R prime, D, D, R, U prime, L, M, U prime. So there you go. There's proof that it works. Now, as you know, there's 43 quintillion cases. So I mean, I tried with a random case today. There might exist a case that this does not work for, but I haven't found it yet. So. All right, so quickly conclude this. So in conclusion, first I started out with a simple two-dimensional model. And from that model, I built a three-dimensional model that the user can interact with. And then I wrote the algorithm, and I wrote the beginner's algorithm, and it was pretty slow. So I came up with the CFOP system, which was a lot faster. And over, like you saw, the worst, best, and average cases and experimental cases, and it really showed up the beginner's algorithm. So if you want to learn more about Rubik's Cube and speed cubing, in fact, check out this book by Dan Harris. I really invite you to take a look at this. This is a very good book. It teaches the algorithm that a lot of fast people use. You memorize all these algorithms. I don't have them all memorized, but if you memorize them all, you can start bringing down your time like crazy. So, the end for this presentation. Any questions?